Again, I'll ask one more time. No questions on any homework or any of that kind of stuff. We did something kind of complicated last time. Hopefully you've had a chance to look at it, make sense of it. It's called the law of Biot-Savart, Biot-Savart. I've got it written up here on my iPad. I'm going to go over it again, and I'm going to actually work a couple more examples with it so you'll see how it's done. And of course, on Thursday of last week, we actually used it to calculate the magnetic field around a current carrying wire that was parallel to the z-axis. And in fact, the z-axis was the axis of symmetry for the wire. So what we discovered is that if you have a wire, let's say vertically oriented along the z-axis with the current running upward in the positive z direction, and you can take your right hand and wrap it around the current carrying wire with your thumb pointing in the direction of the current. And then if you look at each point out here, your fingers are actually telling you the direction of the magnetic field. So right here, they're actually pointing, well, the opposite way. I can't turn my arm around that way, but basically the opposite way. What that turned out to be in the case of the z-axis being the axis of symmetry for the current carrying wire, and the current going upward, and the current going in the positive z direction, that was basically equivalent to if you're on the x-axis. So let's say here's the, I'm looking, well, let's say this is the z-axis. If you move to the right along the x-axis, then that would force, okay, the z-axis, if the z-axis is this way and the x-axis is this way, that means the y-axis has to be pointing into the page for me. So right here next to the wire, the magnetic field is pointing in, which is the positive y direction. If you go back here at the y-axis, which is back behind the z-axis, then at that point, the magnetic field is pointing that way. And if you come over to here on this side, at that point, the magnetic field is pointing out of the page. And if you come out here in front, the magnetic field is pointing this way. That's the same as the theta hat direction that I've been talking about that exists in polar coordinates, as well as in cylindrical coordinates. So that's something we're going to make use of again. So I just want to make sure y'all have that idea of a current carrying wire with a magnetic field at this point, pointing this way, at this point, pointing this way, at this point, pointing this way, at this point, pointing this way. Halfway between this point and this point, it'll be pointing at like a 45, of course. And then halfway between this point and this point, it'll be pointing that way. So it's constantly, if you will, if you imagine going out in a radial direction like this, okay, then it's going to be perpendicular to it. And then radial direction perpendicular to it, radial direction perpendicular to it, radial direction perpendicular to it. Okay, that's the perfect definition of theta hat. So let's start by sharing my screen. Gosh, I'm always doing this to you guys. Actually, it happens for your class worse than the other one, which is really weird because I love 242. And I like 241, but 242 is really like one of my favorite classes to teach. So it's really weird that I yawn in it. So it must be purely a result of my tiredness. So just as a recap, I went ahead and wrote out the law of Biot-Savart along with the accompanying diagram that's so important, because it really is hard to make any sense of this equation unless you, in fact, have a diagram in mind. So the diagram is, you imagine that little black wavy thing is in fact a current carrying wire. You can further imagine that the current being carried in that wire is I, and it's going along the direction that the little red arrow just showed. The little blue vector on the wire is a little tangential differential line element vector that happens to be parallel to the wire at that spot, but also parallel to the current. But also parallel to the current. So that's what the DL is in the figure. I made up this version of the Biot-Savart law with the RP and the RDL specifically because it's a little more concrete on exactly what you do. So in this scenario, you have to imagine there's a point P at which you wish to know the magnetic field. Somebody's got your, one of you guys, I think it might be Matt, has your volume on. I'm hearing everything, the coughing and hollering and stuff of that sort. Matt, whoever else is on there, Christina also, there's a couple of people that looks like they might have their speakers on. So anyways, RP is a vector that points from the coordinate origin, and you make the coordinate origin anywhere you want. And you also make the X, Y, and Z axes point in any directions you want. You just always have to make sure they're right-handed, or, you know, stuff about mathematics doesn't work well. So RP is a vector that points from the origin to the point at which you wish to know the magnetic field. RDL is the vector that points from the origin to the little differential line element DL. And then, of course, you subtract RP minus RDL, because it turns out if you take the cross product of DL with that RP minus RDL, that actually gives you the direction of the magnetic field at that particular location P. So that's what that's about. So last time I did this, as I said, with a current carrying wire lined up along the Z-axis. So I could, for instance, draw that right now, just because we're going to use it in some time. So there's my Z-axis. That'll be my X-axis. And of course, since I chose this to be my Z and that my X, then my Y has to point into the page. So there's my Y-axis. What we're imagining here is an infinitely long current carrying wire whose axis of symmetry is the Z-axis. And as I said, it goes for infinity in all directions. And the current I is going upward. Okay. What we found, for instance, at this point right here, P, was that this vector right here is in fact RP. And if we made this little vector right here, say DL, then this little vector was in fact RDL. And of course, that made it such that this black vector is RP minus RDL. And in fact, from that, you can figure out that, of course, DL crossed with RP minus DL gives you Matt Yule. Matt. Okay, I found a way. All right, so anyways, that vector DL cross RP minus RDL, I think you can see that actually points in the direction we sort of desire. And in fact, in this plane, you can see that the DB vector, which I'll draw in, let's say, a pink color, is actually more or less in the Y direction. Okay, it should be exactly in the y direction. In fact, I just didn't draw it quite as parallel as I wanted. And in fact, if we put the point back here, P, then it would point this direction. And of course, if we put the point P here, then it would be coming out of the page. And again, if we came out here in front of the wire, it would be pointing this way. So that's what I meant by it actually being in the theta hat direction. The theta hat direction is just 90 degrees ahead of the r hat direction. Okay. So let's work on another one today. And the one I want to work on today, I'm going to start off with a black coordinate system. I'm going to try to make it kind of neat. I will say this will be our z-axis. And I'm going to say that this will be my x-axis or my y-axis. And then this will be my x-axis. So this is x, this is y, this is z. And what I'm going to do is I'm going to imagine basically a circle lying in the xy plane whose radius is r, like that. And it has a small but finite thickness like that. Okay. So that's all lying in the xy plane, if you will. Hopefully you can see it a little bit more that way. I'm not really happy with that drawing, but we're going to have to deal with it. So what I am going to imagine to deal with this is I would like to know what is the magnetic field at this point P right here. Okay. So right here, I'm saying dB is equal to question mark. What I'm going to do is I'm going to consider a little tangent vector to this current carrying loop. And by the way, the current in this loop is going that way. Okay. So I'm going to take my little differential tangent vector and I'm going to attach it right here. And I am going to say that, in fact, the end of that is at an angle theta. And of course, it's out, since the thickness of this ring is not appreciable, it's out a distance capital R, which is the radius of that ring. Okay. Now, the way we get that little differential area vector, or excuse me, differential tangent vector, is we allow theta to change by an amount d theta. And then that tells us that dl is in fact equal to r d theta, and it points in that theta hat direction. Okay, remember r hat would just be the vector that continues on radially outward, and the fact that it's a hat means it's 1 unit long. And of course, r hat, we've already worked out before, is cosine theta I hat plus sine theta j hat. Now you can also use the fact that just like this angle from here to here is theta, well, the angle from the y-axis to theta hat is also theta. So this little vector right here is also parallel to theta hat. So I want to write that down. Okay, so you can actually work out by that the theta hat vector is actually equal to, notice it's pointing in the negative x direction, so I have to say negative sine theta I hat, and sine, of course, for the theta is the opposite side, and then plus cosine theta j hat. So that's actually what theta hat is. Now, the vector RP, the one that points to the point P, is in fact this vector that points from the origin to the point P. And I'm going to say that point P is a distance z up above the xy plane. The vector RDL is in fact this vector. So that vector is RDL. Obviously, in order for us to use the law of Biot-Savart, we've got to figure out RP. We've already figured out DL, so that's nice. So let me write down what we have figured out. We have figured out the DL, which is going to be R d theta, and multiplied by the theta hat vector, which is a vector whose length is 1 unit long and is 90 degrees ahead of the r hat vector. We still need an RP, which is a vector that points from the origin to the point P. Can anybody look at this diagram and at least tell me how long the vector RP is?
Is it Z?
Yes. And can you tell me how to make that into a vector? What would you write down as RP the vector?
P K hat.
Exactly. So we're just going to write Z K hat, easy peasy, right? Now, it is a little more complicated to write out what RDL is, but I will give you a little piece of information that might actually help you. In this case, it turns out that if you state it in terms of R hat, it's really, really easy. But normally, most people would find the X component and then multiply that by I hat, and then find the J component and multiply that by J hat. Can anybody tell me what the X component of the vector RDL would be?
Cosine of theta times
Exactly.
R.
Times capital R, right? That's because basically this green line right here defines the Y component, and this green line right here defines the X component of R, right? So for a reason that you might not guess right now, I'm going to go ahead and write it the easy way. And basically, the rule is if you have a cross product in a vector, I mean, inside of an integral or a derivative, you can actually work out that cross product first and then do the integration. And in fact, it's often way easier to do that way. So what I'm going to do is I'm going to say that RDL is the vector whose length is R and points in the R hat direction. You just got to remember that R hat is technically a function of theta. So if it helps, write of theta hat, because that obviously shows you that R. I could say that for any vector anywhere on any circle of radius big R, but the deal is that big R is not enough to nail it down. You also have to have the theta too. That's why I mentioned that R is RDL is R hat of theta. So now that should make it easy peasy. And also it might help you by looking at this. If I draw this vector in red, this vector in red is RP minus RDL. Can anybody tell me what the magnitude of RP minus RDL is? Without even calculating RP minus RDL yet. Can you just look at that figure and tell me what the magnitude of RP minus RDL is?
The Pythagorean theorem.
Exactly. You're going to use the Pythagorean theorem. And what are the two legs that you're going to square? What are the lengths of those? You're right. This is, in fact, a right triangle right here. So there's our right angle. So it's this length, this red length down here, and of course this blue length up here is the other one. So can now someone tell me what's going to be squared under the square root? How about r squared plus z squared? Remember that red vector lying in the xy plane points to this from the center of the loop to the basically the edge of the loop. And I said the loop has a finite but very, very small thickness. So you don't have to consider it being any longer or shorter than r. So that little red vector is in fact a length capital R. And of course, perpendicular to that is a length z that goes along the z-axis. So that's why it's r squared plus z squared square root. So now I've got all the parts. All I have to do is write the b part. So all I have to do now is compute the b. And I think I'll do it in purple because I've never done it in purple before. I can be brown, I can be blue, I can be violet skies, I can be purple, I can be purple, I can be anything you like. Y'all remember that meme? Anyways, stuck in my head still. All right, so B is going to be equal to the integral of dB, which is going to be equal to mu 0 I over 4 pi times the integral of r d theta theta hat crossed with, now here's the part where I might lose you a little bit, but this is the best way to write it. I'm going to say RP minus RDL is in fact z k hat minus r rho hat. And then all of this, of course, will be over r squared plus z squared to the 3/2 power. Because remember, it's a 1/r squared law, but in order to get this into a vector format, we had to multiply it by a vector. That vector is RP minus RDL. So I needed to divide it by another magnitude of RP minus RDL to cancel out the magnitude of that one. All right. So let's take a little sidebar here and write what's going on with this cross product. What I have is theta hat crossed with zk hat minus r hat. That's going to be theta hat. Well, actually, let me write it this way. That's going to be z times theta hat cross k hat minus r, big R that is, times theta hat cross r hat. Now you can look at theta hat and you see that like when theta is 0, theta hat points in the positive points in the positive y direction. When theta is 90, it points in the negative x direction, so on and so forth. So right now where it is, theta hat points sort of, almost like 45 degrees or whatever. But if you do a cross product of that with k hat, you get that points in the radial direction. Are y'all able to see that? So for instance, if you're looking at me, okay, the theta hat is in the XY plane and pointing sort of that way. K hat is in fact pointing up like that. And now my thumb points perpendicularly, of course, to theta hat. It's like that. So it's actually behind theta hat pointing in that R hat direction, just like I've got drawn with that little black R cosine theta equals cosine theta I hat plus sine theta J hat. So that is exactly R. But what about theta hat cross R hat? Theta hat cross R hat, I think you can see, is theta hat's going this way, R hat's going that way. That should be in the negative K hat direction. But remember, there's a negative in front of it already. So you got to realize that's ultimately going to come out positive. Let me make this, I made it a little bigger so we could make better sense of what I wrote. So this one's going to be in the negative K hat direction. But remember, we've got this negative and this negative, which should make it into a positive. Okay. Now, as you might suspect, any kind of R hat vector should integrate to zero, because if you think there's part of the current right there where I've got the R vector drawn, that point that causes a magnetic field pointing outward, then absolutely there's no ifs, ands, or buts about it. But back here in the back, that particular section would cancel out that R out of symmetry. So we know that should ultimately go to zero. But we'll deal with that as we go. So let's go ahead and now do the magnetic field again by substituting in this cross product. I got B is equal to mu 0 I over 4 pi. Now I've got the integral of, now what we found was theta hat cross K hat gave us that R hat. So now I'm going to say this is R Z d theta R hat. And then the other one was minus a minus. So this is going to become positive R squared, because there was already an R there, d theta. And then that's going to be in the positive K hat direction, again, because those two negatives canceled each other out. And now what I've got in the denominator, this is a hat. So I'm trying to make sure you can see that's a hat. And what I have in the denominator, of course, is R squared plus Z squared to the 3/2 power. Okay.
I have a question.
Yes.
Why is it just theta hat that's being that's a cross product with the that second bit?
Okay, because that's the only thing that's a vector over here. So if you look, when you do a cross product is a product between two vectors. In this case, we were basically doing sort of the distributive property. So theta hat first has to cross with the K hat, and then theta hat has to cross with the R hat, just like you do with the FOIL method. Of course, FOIL is when you have two binomials. In this case, we only have one monomial and one binomial. Does that make sense?
And we just plug in the R d theta kind of thing at the end?
Yes. So yeah, it was in front of the integral already. I just chose not to write it down because I tried to keep it as simple as possible. But yeah, absolutely. There was an r d theta there. I just chose not to write it because I figured it would just make it further complicating on the issue. Of
Okay.
course, it looks like it might have had the worst effect and made it worse. Anyways, all right. So we already argued from a symmetry standpoint that any vector component of the magnetic field that pointed in the r hat direction would obviously integrate to zero after you go the full loop. If you wish to see that, all you have to do is substitute r hat in for r hat. In other words, put in that cosine theta I hat plus sine theta j hat, and you'll see that you're basically going to be integrating the r and the z and the r squared plus z squared to the 3/2 in the bottom. All that's going to come out in front of the integral, and you're basically going to get the integral of cosine theta d theta from theta equals 0 to 2 pi. Clearly that's 0 because cosine has just as much positive as it does negative from 0 to 2 pi. And then the other term is going to be d theta sine theta. So that too is going to integrate to 0. So that whole first term from a physical standpoint, now I've explained to you from a mathematical standpoint as well, will not survive. So this part of the actual integral shall go to 0. And all I'm left with is the r squared d theta k hat. So my next step is equal to mu 0 I r squared over r squared plus z squared to the 3/2 power. And actually, let me write that a little, well, let me write that a lot better because that pretty much sucked. Sorry about that. So yeah, this kind of sucks. So let me write it a little better. So I'm going to say equals, make it a little smaller so I can see everything that's there. I'm going to have a mu 0 I hat. I don't know why I just said I hat. A mu 0 I times a capital R squared over a 4 pi. I don't want to do that. I want to do R squared plus Z squared to the 3/2 power. Notice none of that's playing any role in the integral. And notice also that where I showed you that r hat vector integrating to 0, remember r hats and theta hats and phi hats and everything essentially but I, j, and k hat have to be dealt with when you have them in a calculus formula. You can actually pull the I hat, the j hat, or k hat from inside of an integral out in front of it and then back in if you want as well. Nothing ever happens with that because that is truly a constant vector. But the r hat vector, you can't process in an integral without breaking it back into I hat and j hat. That's what ultimately led to that integral being 0. The rest of the stuff, notice, other than the d theta, is not playing any role in the integral. So all I have left now is that stuff times the integral with a k hat. Yes, sir.
Why does it equal 0?
I'll show you in a second, but basically once you put in that r hat, remember the r, the z in front of it, and the r squared plus z squared to the 3/2 below it. That's all can come right out in front of the integral. But that r hat has to be put in, and you know from this definition in the bottom left that that means cosine theta d theta I hat. The integral of cosine theta from 0 to 2 pi is 0, so that's going to get rid of the I hat component. And then the integral of sine theta d theta from 0 to 2 pi is also going to give you 0. So the j hat component is also going to be 0. So that's why I argued mathematically that that term in the integral is going to be 0. Physically, we said it should be 0 just by the symmetry of it, because if anything caused a r hat component right there at that theta, if we just considered theta plus 180, that little blue dot that I drew back there in the back, that little segment of wire would in fact cancel out the r hat component that's happening on the other side. So that was the physical reasoning why. Does that help you?
Yeah.
Okay. So all we have left now, believe it or not, from that big, ugly, scary problem is basically just a d theta being integrated from theta equals 0 to 2 pi. So you can see what happens. Basically, the pi cancels out with the pi in the bottom. The 2 cancels out with the 4 in the bottom, leaving a 2 in the bottom. So now I'm going to have mu 0 I times r squared over 2 times r squared plus z squared to the 3/2 power times k hat. And that is actually equal to our magnetic field at any height z above the xy plane. Luckily, you can make that kind of big. You can also see if you isolate it down to z equals 0. So for z equals 0, that means you're actually in the center of the single loop of current carrying wire. Then the magnetic field is in fact going to be, notice the z drops off, we get r squared to the 3/2 in the bottom. That becomes r cubed in the bottom, and r cubed in the bottom with r squared on top ends up giving us mu 0 I over 2 r. And again, I'm going to say it's k hat for that particular instant, but by symmetry, you realize you're actually getting theta hat direction. Excuse me, not that. No, that was the other problem. Let's not do that. Okay, there it is. Looking for my erase. I'll go ahead and put that K back in there. Blue. So that's the neat expression we got for a single loop. And that becomes helpful because the next Biot-Savart problem I'm going to do, we can make use of that. In fact, that's going to be, it turns out really, other than that one problem I solved on Thursday, you're basically going to have one type of problem that you can really solve from Biot-Savart, and it's that infinite line like I did Thursday, the single loop like I just did today, and then variations on the single loop, but variations specifically where z is equal to 0. So that's the next example I'm going to show you. So again, I'm going to zoom in on this just because obviously I wrote that super small to fit it on the page, but I want y'all to be able to look on the video and actually see what I wrote for the final result. So that's what we ultimately got. That is the right answer. You can look, your book solve the same problem. They do it much differently. I try to show you what's going on with the mathematics because I think the mathematics, though it seems hard, is not that difficult, as long as you're at least following or have some kind of an algorithm that you're going to work. And the algorithm I've just given you is you take the law of Biot-Savart, you identify a DL vector that happens to be like a little tangent vector to a small part of the current carrying wire, and that points in the same direction as the current is going. That vector is DL, and that's part of the formula you have to fill in. In our case, it was RD theta theta hat. 2, you find a vector that points from the origin of your coordinate system to the vector DL, and that's called R sub DL. 3, you find a vector that points from the origin of your coordinate system to P, the point at which you wish to know the magnetic field, and that vector is part of the formula too. Then you, number 4, calculate RP minus RDL. As you can see, sometimes there's smarter ways than others to do it. In this case, ZK hat minus R hat was the smartest way to do it, because it allowed me a very easy distribution or distributive property with the cross product. 5, you have to compute the length of the vector RP minus RDL, which sometimes you can just look at the diagram and make it easier than by doing it. But if you ever get stuck, of course, you're going to have to just do it brute force, but you almost always find sine squared plus cosine squared coming in to help you, because everybody knows sine squared plus cosine squared is equal to 1. So any questions on that? That is not a trivial problem by any stretch of the imagination, but with a good algorithm, which is what I just laid out there for you, and a good formula, which is what I gave you up there. By the way, that formula is not in your book, but it is one you're allowed to put on your equation sheet. So keep that in mind. But with a good formula and then a good algorithm that tells you how to apply the formula, then you can easily do even the most complicated problems. Now, these are ones we can actually do by actual integration by hand. If you're doing something more complicated, then obviously you'd say, okay, well, maybe I can't do this one by hand. And you'd basically write computer code, write some kind of computer code to do the integral for you. Now that computer code could be something you make up yourself, because we learned in Calc 1, basically an integral is a limit as delta x goes to 0 of infinite sum of Riemann rectangles, basically. So you can make those rectangles as small as you need to, at least in width, until the function doesn't vary that much in the height, and then just add them all up. And then even though you're not physically going through the calculus of taking a limit, you're realizing that by going at small enough interval, you are treating the function as if it has been integrated. So, and there's whole books written on this. In fact, there's a book called Numerical Recipes in Blank by Saul Tucholsky and 2 other authors whose names escape me, but mainly because I met Tucholsky one time. But anyways, he's one of the authors, and it's numerical recipes in C, numerical recipes in Fortran, and numerical recipes in Pascal. So that's sort of one of the Bibles of writing code for physical problems, and you can learn all you need from that. There's other books too, more modern ones, and I would hope by now someone's written one on C++ or something like that, but really you don't need any more than C, and C++ doesn't differ too horribly much from C, other than its object-oriented nature. So any questions about any of that? All right, so I've given you this formula, this Biot-Savart law involving DL, RP, RDL, RP minus RDL, magnitude of RP minus RDL, and I've given you the algorithm for it, so you should know how to do it. Now let me introduce you to the other type of problem that you can solve, and you'll see there's several of them in the end of your chapter of your textbook. Let me start by drawing a little coordinate system. This little coordinate system will, of course, be in black. And I am going to make it two-dimensional because life is really easy in 2 dimensions. And now I've made it nice and pretty, so I'll call that the x-axis. Well, I'll ask that my program stop changing my drawing into a erasing. Okay, so what we're going to do here is we're going to imagine a current carrying wire that's going to come in from the right-hand side, carrying a current from right to left. So basically what I'm going to say is this is a current carrying wire, and it's carrying a current this way. Okay. And then right there, what happens is it goes into an arc of radius, obviously 4 blocks there, and continues on like this. So this is supposed to be a half circle, basically, even though it's obviously probably a crappy version of a half circle. And now I'm going to go back out to here and say that this now follows that kind of circle. And now I'm going to go back in to here and let it follow this kind of circle. And then go back out. So what I'm saying is in this top part, the current is this way. Then the current goes around there, then around there, then around there, and up there, and around there, and then back out that way. Okay. And I drew it a little bit off of the axis here, just so you could see what it was doing, not because it's not actually against the line or anything. I just wanted you to be able to make sense of what I was saying. So I drew it this way. And I tried to draw the wires thick. One, because it's more room for error. And 2, just because it makes it a little bit easier to see. So what I'm going to do is I'm going to assume that this is radius R, and that this, let me get rid of the part of this. Anyways, okay, got that. Okay, that did not help all my drawing there. This one, on the other hand, is radius 2R. And this one, on the other hand, is, notice the first one was 4 loops. This part right here is radius R over 2. So I also need to reestablish that the current is going this way here. Okay. Now, the way the law of Biot-Savart works is that basically we have dB is equal to mu 0 I over 4 pi times dl crossed with rp minus rdl. Now, rp points to the position at which you wish to know the electric field, or excuse me, the magnetic field. And RDL points to the little tangent vector of the current carrying wire. So there's something you need to think about. Remember that A cross B in magnitude is the magnitude of A times the magnitude of B times the sine of the angle between them. And remember, of course, that sine looks like this. where this is 360 degrees or 2 pi radians. This is 180 degrees or pi radians. And this right here, this peak, corresponds to pi over 2, which is also equal to 90 degrees. In other words, sine peaks at 90 degrees, whereas cosine 0 at 90 degrees. So if we look at the different parts of this problem we're trying to solve, I'm going to go ahead and label them with this fancy green color. This is going to be part 1. This is going to be part 2, part 3, part 4, part 5, part 6, and then part 7. So if I take time and write part 1 here, what I see is RP, since P equals 0, 0, implies RP is equal to 0, 0. Okay. Then you've got, instead of DL cross RP minus RDL, you've got now DL negative cross with RDL. So in other words, you're taking the cross product of the line element with the vector that points to it. So for part 1, we could say DL is equal to negative DXI hat, but you'd see that RDL is in fact some XI hat. So it's literally 2 parallel vectors being crossed, and the cross product of parallel vectors is, of course, 0. Does that make sense for part 1? I can draw the vector up here. Let's do that. Let's do it. I'll change the colors. I'll do a color like let's do this white vector. So in this case, whoa, surprisingly, white does not show up all that well. Yep, white sucks. Anyways, white was not. Let me go back to that cheesy pink vector. Okay, so that is RDL, right? And then, of course, DL is just this little doohickey. So you see that that's not going to do any good. You can also see, however, that in part 3, so let's go back to this. In part 3, you see that DL cross RDL again is going to be 0. Does that make sense to everybody? Everybody see why that one's 0?
Is it because they're like opposites?
Yeah, well, so the RDL is going to point in the negative I hat direction, right? Because it's got to point from the origin to some point on the part of the circuit 3. And DL is going to point, in fact, in the positive I hat direction. But that means the angle between them, again, referring to this version of cross product, the angle between them is 0. And of course, the sine of 0 is 0. So just like the last time, the sine of 0 is 0 for 1. The sine of 0 is 0 for, or excuse me, the sine of theta is the sine of 0 for 3 as well. And I think you can see that's also going to be the case for 5 and for 7. So for number 5, actually, for number 5, I'll put it back over here. The DL cross RDL is actually going to be, in this case, the DL is going to be like a dy j hat, and the RDL is going to be a negative y j hat. When you cross those two, you're clearly going to get 0 because they're parallel to each other. And then when you do 7, you should be able to see that DL cross RDL, the DL in this case, which has to point in the direction of the current, is in fact dx I hat, and then the RDL is in fact x times I hat. So when you cross product those two, you get 0, which means the magnetic field due to that part is also 0. Now let's attack part 2. So part 2, DL is going to be R d theta theta hat. RDL is in fact going to be just R times R hat as a function of theta. RP is still 0, so what you end up getting is dB is equal to mu 0 I over 4 pi integral of, now R d theta theta hat cross R hat. And technically, let's see, is that R hat the right direction? It's got to point from the origin to the DL. So yes, RDL is right. But it's supposed to be negative because of the RP minus RDL. So sorry about that. Let's fix that real quick. So I'll put in a little parenthesis here and say this is negative R hat of theta. And then, of course, the length of RP minus RDL, since RP is 0, the length is just obviously R. So this is going to be R cubed down here. So ultimately, I'm getting mu 0 I over 4 pi, R squared's up top. We're getting a negative here. Theta hat cross R hat points, in fact, in the negative K hat direction, which would be into the page, but there's a negative in front of it. So I'm going to say positive K hat. And R down here is all that survives as far as that goes. And I just get the integral of d theta from theta equals 0 to pi. As you might suspect, remember the last time we did one complete loop, and in one complete loop, we got mu 0 I over 2R. down there in the bottom right. See? So if we do half a loop, I suspect we're going to get mu 0 I over 4r. And in fact, that's exactly what you see happens, because the integral from 0 to pi is just going to give you pi. That's going to cancel out with the pi in the bottom, and we still have the r. So in fact, we're going to get mu 0 I over 4r k hat. So this is B for number 2. Anybody want to take a guess at what B for number 4 is? Okay, I'm going to write it down and see if y'all can make sense of it, this being the answer. So B sub 4.
Would it just be the other one times 2?
Times 2 are, well, let's work it out. You might be jumping ahead of me algebraically. So for starters, the R is going to be switched off with 2R. So that's going to make it like, if it was a whole circle, it would be over 4R. But since it's the quarter circle, it's going to be 1/4 of that, I think. So I'm thinking more like a 16th or something. Let's check. What I get, or what I'm thinking it's going to be, is, notice the current still points in the right direction for it to be in the positive k hat direction. I'm thinking it's going to be mu 0 I over, now in this case, we're actually integrating from pi to 3 pi over 2, which is 3 pi over 2 minus 2 pi over 2, which is pi over 2. So I'm going to get mu 0 I over 8r just for that part, but then I'm going to get another 2 because it's not r, it's 2r. So yes, I'm thinking I get 16r k hat for that one. What I'm using here again is one whole circle implies B is equal to mu 0 I over 2r. In this case, it was a quarter circle, which implied B would equal mu 0 I over 8r, but r was replaced with 2r. So it became B equals mu 0 I over 16r. Okay. How about, can we do number 6? So if you guys can get number 6. And I say guys again, that's not a gender thing for me. So please, people that don't assume themselves to be guys, do not take offense.
Would it be 2 mu 0 I over r?
Yeah, it looks like, since it was, if it would have been a whole circle and the r is r over 2, then that would be mu 0 over r, just because the twos would cancel out. But in this case, it's a quarter. So instead of us having mu 0 I over r, I think it's going to have to be mu 0 I over 4r. Was that what you reached as well, or did I mishear you?
That's not what I said, but I get it.
You say, okay. Hopefully I'm right. And we, you should definitely go back and work these out to make sure. Once you work them out, maybe once or twice, you really shouldn't have to do it much anymore. But in this case, I'm going to say the result again. Notice that if I grab that part 6 with my right hand, such that my right thumb is pointing in the direction of the current going up and to the left, if I wrap my fingers around that part 6 wire in the center of the circle, my fingers are pointing out of the page, which is the positive k-hat direction. So just like the other two parts, this is a positive k-hat direction. I'm going to say, I'm going to say mu 0 I. And now since the r was r over 2, what I could do is I could just put 2 over r over 2. That's what it would be if it was a whole circle. But since it's only a fourth of a circle, I'm going to say times 1/4, like that, and then put my k-hat. And in this case, I now get, notice the r over 2 and the 2 here cancel out. So I end up getting mu 0 I over 4r k-hat. So finally, I can say the B at the origin is equal to, now I've got mu 0 I over 4r plus mu 0 I over 4r. That's 2 mu 0 I over 4r. And then if I wanted to, I could make that 4r in the bottom a 16, so it would add up with this. I just have to multiply by 4 and 4. So I had 2 mu I over 4r. That's now going to become 8 mu I over 16r plus 1. So I've got now 9 mu 0 I over 16r k-hat should be my final result. Assuming all my arithmetic's correct, because really what I'm doing is mu 0 I over 4r plus mu 0 I over 4r plus mu 0 I over 16r. So everybody follow that? All right, so that's one of the supposedly easy applications of Biot-Savart law. You'll see your book has examples that look like this, and where the current's going this way, this way, this way, this way, or around the other way if you want, and stuff like that. So they can do that all day long, and you can just keep working through it. You just got to realize any of the, if you're asking for any current or any magnetic field due to or are at some point parallel to these straight lines, then obviously that part's always going to be 0. And then the other parts are going to be like this. So just remember, for a whole loop, it looks like you're going to get mu 0 I over 2r as we worked in the previous problem. And then obviously for a half loop, that's going to get half the size. For 2 loops, that's going to get twice the size. For a third of the loop, it's going to get a third of the size, so on and so forth. Now, here's something neat that we can do. It turns out that there is a easy version, just like we had that tough Coulomb's law, which basically said E was equal to the integral of dE, which I said was 1/4 pi epsilon naught integral of dq, and then I said rp minus rdq over rp minus rdq cubed. That was pretty difficult, but we could do it. And then I said, well, wait a second. It turns out there's a law called Gauss's law that says the closed integral of E dot dA is equal to Q enclosed over epsilon naught. And that made, as long as certain symmetries were there, that made it possible for us to extract the integrand E by making a hypothesis of what the E field would be, the E field being, you know, a physical construct that we have some understanding of symmetrically by using Coulomb's law. So as long as we had spherical, cylindrical, or infinitely large planar symmetry, we could hypothesize the shape and direction and magnitude and what variables the magnitude depended on for the magnetic field, I mean, for the electric field, and use that Gauss's law to compute the electric field. Well, it turns out just like that, and the fact that B is equal to the integral of dB, which equals mu 0 I over 4 pi times the integral of dl cross rp minus rdl over rp minus rdl cubed. There is another expression that can make our life a little easier, and this one's called Ampere's law, and it says the closed integral of B dot dl, notice that's a dl instead of a dA, is equal to mu 0 I enclosed. Now, normally what I do is I work just the left-hand side for an infinitely long straight current carrying wire carrying a current I at a distance r away, because we know that magnetic field, we worked it using the law of Biot-Savart and found that the magnetic field was mu 0 I over 2 pi r in the theta hat direction. So I normally do that and then find out what their what the right hand side is. I'm not doing that for y'all. I'm just going to jump in and show you how we can do a problem. So let's imagine a coordinate system again. This time I'm going to put my coordinate system in a sort of odd way. I'm going to say this direction right here is the x-axis. Coming out of the board is the y-axis, and going to the right is the z-axis. So there's my z, there's my x, and there's my y. And what I'm going to imagine is, in fact, a ginormous current carrying wire that goes on for infinity and is centered on the z-axis. Like such. Whoa. So it goes on for infinity this way and this way too. I'm going to say it, in fact, carries a current I this way, and the I is uniformly distributed which means that J, the current per unit cross-sectional area A, is equal to a constant. And what I'd like to know is, what is B everywhere? Okay, so I want to know, what is B everywhere? So here's how you use Ampere's law. Ampere's law is a line integral on the left-hand side, not a surface integral, but it is expected to go over a closed line as opposed to just any line. So it's got to be a loop, basically. So I know from symmetry that if I had a wire that was infinitely thin running along the z-axis, I would expect a magnetic field that points in the theta hat direction. So my hypothesis is, here's my solution. Actually, I'll do my solution in that purple again. I really like that purple. So solution. So I'm now saying for, let's call this radius right here R. So I'm saying for R less than big R. So for that R less than big R, what I'm doing is I'm saying my hypothesis is that B is equal to some B that only depends on the polar coordinate R. In other words, that's the only variable that would make it get smaller or larger, and that it's points in the theta hat direction. Now I'm going to draw a circular loop of radius little r, and that's going to be called my Amperian loop. Just like the last one was a Gaussian surface, this is an Amperian loop. And as long as I traverse or integrate this Amperian loop in a direction consistent with the right-hand rule, and the I is consistent with the right-hand rule, then the I will be positive, meaning if my fingers are curling in the direction that I'm integrating around that loop, my fingers on my right hand, and my left thumb points in the direction of the current, then that current is positive. If the current goes the other direction, then that is a negative current and has to be counted that way. So the left-hand side of Ampere's law becomes the closed integral of B dot dl, which is equal to the integral B of R theta hat dotted with, as you might suspect, R d theta theta hat, right? Because basically I'm letting this little bit be theta, then this little bit right here will be d theta, and then of course this little bit right here would be r d theta. Now, using the linearity of the dot product, that means I can take that b of r, and I can take that d theta, and I can take that r and put them all out in front, and then I have times theta hat dot theta hat. Can anybody tell me what theta hat dot theta hat should be? One, exactly. Okay. And just like we did with Gauss's law, we want to make sure that the magnetic field is either constant along the Amperian loop, or is actually perpendicular to it. That way it'll all disappear and I'll only get B times the length for the left-hand side. In this case, as you can see, I do ultimately get, since R is a constant, I can go ahead and pull that out, and I'll say, oops. I'll say B of R times the integral of d theta from theta equals 0 to 2 pi, so that the left-hand side just becomes closed integral B dot dl is equal to 2 pi r times B of R. Oops, didn't need that last part. Now the right-hand side is a little more complicated because we know the total current I going through the loop, but we don't know the current going through that little Amperian loop. So we use the fact that J equals a constant, and J, of course, is I over pi r squared, but that also has to equal I enclosed over pi little r squared. So we can conclude that I enclosed must be equal to r squared over big R squared times the total current I. Therefore, the right-hand side, which is mu 0 I enclosed, is equal to mu 0 I times r squared over big R squared. So now we can say left-hand side equals right-hand side. And in this case, we get 2 pi r B of R is equal to mu 0 I r squared over big R squared. Clearly, that square cancels out with this. And what I end up having is B of R, or I just should say B. B is equal to mu 0 I times R in the theta hat direction over 2 pi big R squared for R less than R. Now, class is over officially, so you guys are free to go. I'm going to finish out this one example, which is handling the second part for R greater than R. But like I said, you're free to go. It'll be on the recording, so you won't miss anything. But anybody have any questions? I'll wait for the last person to ask any questions, then I'm going to finish this up and post the video as soon as it finishes processing.
Professor, I do got a
Yes.
question, but it's not with the lecture. It's about the
Yes.
test, the latest test
Okay.
that happened. I don't know if you got the email I sent you like last week, but I said that I wasn't able to do the test.
Oh, okay. So you
last
missed
week.
that last test that we had?
Yeah, test 2.
Okay. I will open it back up. Let me write your name down so I don't forget. I'll open it back up and give you till the 12th to get it done.
The 12th. Okay.
And that's 12th of March, of course.
12th of March.
And Jonas.
Yeah.
And it's test 2, you say?
Yes.
Okay, I'll open that up tonight. And I'll give it, and I'm not going to take any points off because I haven't gotten all my stuff done in time this semester either. So I'm going to be a little nice to folks right now.
Okay. Thank you so much.
Okay, you're welcome. Anybody else have any other questions? I'm going to try to finish out this. This other part's actually pretty straightforward. We're going to end up getting exactly the same thing. We're going to get the integral of B of R theta hat dot R d theta theta hat, which ends up giving us 2 pi R B of R. Only the right-hand side, since we're now dealing with an Amperian loop that's much larger and in fact is completely outside with a radius r, then the current is the total current. So I get mu 0. Oops, I should probably stick to purple since I'm calling the solution purple. Is mu 0 I. So left-hand side equals right-hand side gives me this wonderful 2 pi RB of R is equal to mu 0 I. R B is equal to mu 0 I over 2 pi R theta hat, which, by the way, is exactly the same result we got when we did it with the law of Biot-Savart on Thursday. So I apologize for it being that small in the corner there, but it's just mu 0 I over 2 pi R, which, as I said, was the exact same thing we got on Thursday. Now, what we normally do with such a problem, just like we did it when we did a uniformly charged cylinder or a uniformly charged sphere, is we calculated the electric field inside and out with Gauss's law. We're going to do the same thing now and do the little graph like we did then, only we're using, of course, Ampere's law. So if I make a little graph, if you will, of the magnetic field as a function of R, like so, I would have R, the radius, right here. I would have mu 0 I over 2 pi big R right here. And what we'd see is that the magnetic field would increase linearly until it got to R equals big R. That's what this equation shows. And then from there on out, this equation shows that it falls like 1 over R. So that is what the magnetic field in and are around a cylindrical wire with current uniformly distributed throughout. By the way, that is not the normal scenario with current carrying wires. Oliver Heaviside used to talk ad nauseum about how the vast majority of the current was on the outside edge or even on the skin of the actual wire. And in fact, most of the energy is really in the magnetic and electric fields around it, which have almost no desire to stay within the housing of the wire. So that's a whole different issue. But anyways, it's very unnatural to consider a uniformly distributed current density like that. But I mean, I guess you could force it. Normally what happens is you get like most of the current on the outside edges and a small amount on the inside, stuff like that. So anyways, that's it, folks. There's 2 other types of examples I need to work with you. You can find them in your book. I will do them next time as well. But that's for a solenoid, SOLENIOD, and a toroid, TOROID. And you're going to use some very specific numbers there. For instance, when dealing with a solenoid, there's a number lowercase n. That means the total number of turns, which would be capital N, divided by the total length, which we often call capital L. So that little n would be, in fact, capital N divided by capital L. Then when you get to the toroid, the thing that matters really is the total number of turns, capital N. So in that case, you're going to have a formula that involves capital N, and it also involves the radius of the toroid. The toroid is really a donut, if you will. So if you can imagine taking a Homer Simpson donut that's perfectly donut shaped, as opposed to having any little creaks and crags and bumps and folds and stuff like that in it, but just imagining it being a cylinder that you got hot enough till you could take the 2 ends of the cylinder and bend them around and glue them to each other face to face. that would be the kind of donut we're talking about for a toroid. Now you take that donut and you smoothly wrap wire around it in a conic and sort of a helix way. That's it, not a conical, but a heliacal way. So you're going around in a helix or like a spiral, that sort of thing. That would be a toroid. Okay. And it doesn't necessarily have to have anything in there for the donut. It could just be air, but usually it does have like some iron or something like that in it. All right. Well, that's it, folks. That ends today's class. I've now shown you 3 total very robust Biot-Savart law applications. And then I just showed you one pretty good intro to Ampere's law. I did not motivate Ampere's law like I did with my lecture class. And the only way I would do that really is just to start off with the left-hand side, the closed integral of B dot dl, and work out that for an infinitely long wire carrying a current I and trying to find out what that integral is at a distance r away. And what I'd end up turning out is, in fact, basically mu0 times the current of the wire. So if I made the loop outside of the wire, then the total current would be the current of the wire. So that's the part that I skipped. Obviously, you can make that up yourself. You can look at it in your book, or you can even look at it in some of the older videos from my YouTube channel. I seem to have one student left. Do you have any questions, Joseph?
No, I don't really have any questions. I just want to let you know I did text you that one night, Friday night, about the job I might be starting. I might be starting, I may not. I'll be here this Thursday night, but tomorrow I'm talking to somebody about it. I may not get the job, so I just might be here on Thursday nights. I don't know yet. I'll text you with any updates, but I most likely won't get it.
Yeah, I'll work with you. Like I said, I hope you can keep up. It's really hard to motivate yourself to watch videos that you're not actually taking a part in. So the good news is, yes, the videos will be there. The bad news is you won't be interacting with me in real time. But that's okay. Like I said, you can always set up Zoom appointments with me or even face-to-face appointments on campus, and I'll work with you as much as I can to make sure you still not only pass, but hopefully make a A or something.
Right. All right. Well, thank you very much. I'll keep in touch with you. All right.
No problem. Thanks, Joseph. Have a good day.
Yep, you too.
Bye-bye. And that's all she wrote about that. Say bye-bye.